You know, every single time it rains, this incredible force of nature gets unleashed. It's a force that's powerful enough to carve out canyons, but it's also gentle enough to sustain life. Today, we're going to dig into the world of runoff and water erosion, which is truly nature's double-edged sword.
So, let's just get right to it. The big question we're tackling today is this. Is all that water flowing over the land a good thing, or is it a bad thing? In these two pictures, side by side, they tell the whole story, don't they? On the left, you've got a huge problem for a farmer in Iowa, precious topsoil just washing away. But on the right, in Uganda, that exact same process is the solution. It's a resource they're capturing to water their crops and keep their community going.
All right, so let's officially kick things off. Section 1, runoff, good or bad?
So yeah, like we just saw, it really all comes down to where you're standing. For that farmer, runoff means losing money, losing soil, and polluting nearby streams. But if you're in a dry region, whether it's in sub-Saharan Africa or even parts of Australia, that very same water is like liquid gold. It's something to be carefully collected and saved.
Okay, so how does this whole process even get started? Well, that's what we're digging into in Section 2, how erosion begins.
I love this slide because it makes something that sounds complicated super simple. Basically, water starts flowing over the ground for one of two reasons. The first is what scientists call infiltration excess. Just think of pouring water on a sponge way too fast. It can't soak it up, so it runs off. The other reason is saturation excess. This is when the sponge is already completely full of water. It just can't hold another drop.
So once that water starts moving across the surface, that's when the process of erosion can kick in. And it really just comes down to three simple steps. First, detachment, then transport, and finally, deposition.
Detachment is that critical first moment. It's the instant a tiny particle of soil gets knocked loose from its neighbors. This can happen from the surprisingly powerful impact of a single raindrop hitting the ground, or just from the force of the water flowing over it.
Right. So once that soil is on the move, the erosion can look really different depending on the situation. Let's get into the various forms it takes in Section 3.
We're going to start with what's called sheet erosion. And this quote here, wow, it really nails why this type is so dangerous. It calls it insidious. And that's because it's sneaky. It's not some dramatic flood. It's just this thin layer of water moving across an entire field, slowly, quietly carrying away the best soil, sometimes for years before anyone really notices.
And this is what that sneaky erosion does over time. Just look at the difference here. On the left, you've got this beautiful, healthy soil with 16.5 inches of that rich black topsoil. Now look at the right. After years of sheet erosion, more than a foot of that life-giving soil is just gone, vanished.
So what happens next? Well, that sheet of water doesn't stay a uniform sheet for long. It starts to find little pathways to concentrate its power. And that's when you get what you see here, rill erosion. It's almost like the water is getting organized, forming these tiny little rivers.
And if you don't stop those little rills, they grow up. They become this, gully erosion. And we're not talking about something you can just smooth over with a tractor anymore. No way. These are huge gashes in the earth, permanent scars that totally change the landscape.
And in the most extreme cases, remember that completely soaked sponge? Imagine that sponge is the soil on a steep hill. At a certain point, it just lets go. The whole thing gives way, leading to catastrophic landslides. This picture, it's from El Salvador in 2001. An entire residential area was buried, and sadly about 585 people were killed. It's a heartbreaking reminder that the stakes here can be incredibly high.
Okay, so when it can be that destructive, you have to wonder, how can we possibly get ahead of this? How can we see it coming? Well, that brings us to Section 4, predicting the flow. You see, the whole game is about prediction. If you can predict it, you have a chance to manage it. Scientists have been working on building models to do just that for decades. And let me tell you, those models have come a long, long way.
Let's look at an early attempt, a model from the 1950s called the curve number method. Now, see that straight diagonal line? That's the goal. That's a perfect one-to-one prediction. Now, look at where all those little dots are. They're all over the place, right? Each dot is a real storm. And as you can see, the model's predictions were often way off the mark.
Okay, now, check this out. This is a modern model called WEP. I mean, what a difference. The dots are hugging that line so much more tightly. It's a huge improvement in accuracy. So why is it so much better? Well, WEP is based on physics. It's not just making an educated guess. It's actually calculating the real-world forces at play, like the impact energy of raindrops or the hydraulic power of the flowing water. It's simulating what's actually happening, and that makes it a total game changer.
And this kind of accuracy didn't just happen overnight. The wet model was built on a mountain of data. We're talking decades of research, information from over 50 different locations, and tons of experiments like this one, where scientists literally created their own rainstorms to measure every little detail. It was a massive undertaking.
So, we've got this amazing, high-tech model. Problem solved, right? Well, not exactly. And that brings us to our final section, the future of forecasting. Because, at the end of the day, we're trying to predict nature, and nature is chaotic and complicated, so even our absolute best tools, as good as they are, still have their limits. They're not perfect.
The wet model, for all its power, still has some quirks. It tends to overestimate the runoff from little rain showers and then underestimate it for the really huge downpours. And get this, for any single storm, its prediction for how much soil will be lost could still be off by as much as 83%. That's a massive window of uncertainty.
So really, the big takeaway here is that the job isn't done, not by a long shot. There's a real urgency for scientists to keep pushing, keep refining these tools. Because when we're talking about losing our topsoil, that's something you just can't get back.
And all of this leaves us with one heck of a question, doesn't it? We know runoff can be both a blessing and a curse. We know we can't predict it perfectly. So the real challenge for all of us is, how do we best manage our landscapes to protect what is arguably our most essential and definitely our most fragile resource, our soil?